Okay, can you see my screen?
Yes.
Okay, awesome. Let's see. Oops. Okay, hi everyone, my name is Chris Yang, and today I'll be giving you a talk about some of my recent work looking at how practice drives the automatization of complex motor tasks. And I think that the work here has some relationships to the presentation that Fred Daniel just gave, which we'll get into in the presentation. So people can become experts in performing complex motor tasks through extensive practice. And practice causes task behavior to change in a number of stereotypical ways, including the emergence of skilled action selection, the habitual selection of well-practiced movements, and the performance of the behavior requiring fewer cognitive resources. And this set of behavioral features has been referred to as automaticity. And currently, it is unknown whether a single or multiple changes in neural representations give rise to each of the behavioral features of automaticity. And while the former theory would predict that the features should emerge with similar time courses during learning, the latter theory would predict that the features can emerge with different time courses. So to disentangle these theories, we examined whether these features emerge with different time courses in a complex motor learning task. So we had healthy participants learn to control a bimanual hand-cursor mapping over either 2, 5, or 10 days of practice. And this mapping was similar to the one that Fred Daniel presented before. And on each day, we assessed how skillfully participants could use this mapping while making point-to-point reaches. On the final training day for each group, we flipped the bimanual mapping to assess whether participants would habitually persist in using the originally practiced mapping. And finally, we tested the extent to which participants relied on spatial working memory to use the bimanual mapping in a dual task setting, which is a measure of cognitive load. So first, we saw that movements became smoother and were directed straight towards the target with practice, as can be quantified using initial movement direction error, which suggests that people became more skilled at using the bimanual mapping with up to 10 days of practice. Next, when we applied the flipped mapping, we found that all participants generated movements that would have been appropriate under the originally practiced mapping, but not under the flipped mapping, as is demonstrated by this movement aimed towards a virtual mirror target instead of the real target. Moreover, all three groups express a similar strength of habit as quantified by the percentage of movements aimed towards a virtual mirror target. And lastly, to assess reliance on spatial working memory, we had participants perform a Corsi block tapping task, which involved memorizing and reporting a sequence of targets that appeared on a screen by making reaches towards those targets using the learned bimanual mapping. And we found that during the Corsi task, bimanual reaching accuracy did not improve with practice and was less accurate than that for vertical movements. And while these data may be consistent with the idea that control of the bimanual mapping still relied on spatial working memory after 10 days of practice, the presence of a dual task effect and the vertical feedback sort of confounded these results, and further experiments are needed to make a more definitive statement about the reliance on spatial working memory. But in summary, our results suggest that different changes in neural representations support the emergence of skill and habit during learning. Now, we've also provided some preliminary evidence that this may also be the case for reductions in cognitive load. And finally, I'd like to acknowledge the people involved in this project as well as funding. Thanks very much.